All right, let's talk a little bit about this problem. And so we're going to have to construct some things. So sometimes we have to do a construction with an auxiliary line, which we've done a few times. And sometimes we have to do constructions with like bisectors and things like that. There was actually a reason that we learned this, so make sure to go review those things. And I might do another review video whenever I get a chance. But one thing we want to do is in the figure on the right, we're saying that AB, this line, is parallel to DE. And you can see that with the little symbols that are right there. So you can either have them in words or symbols or both. That symbol right here means parallel to. And same thing for these two lines right here. But our thing is that we want to prove that B equals E, that they are congruent. So this thing gives us a hint of extending BC and ED. So that's a great hint because we start with B and we can extend this to keep going on. Now, I like that because I like making little auxiliary lines. Now, it has to go with some sort of thing on your graph when you make the construction. You have to be able to show why. So in this case, an extension is allowed. We extend them until they intersect because they are not parallel to each other. Notice AB and DE are parallel, so they will never intersect. But since BC and ED are not parallel, as you can even see from here, we can extend them. So we don't actually have to have the graph drawn to scale for this. We just need to say that at some point, if they are not parallel to each other, they will cross and they will make an angle. And that angle is going to help us a lot. So maybe to make it a little bit more visible, this is the part that we extended, and this is the part that we extended. All right, so when we're trying to prove this thing, we are given that A, B, and D, E are parallel, and we are given that B, C, and E, F are parallel. So often it's good practice to take this and write it and then say it's given. So often that's good, just to remind somebody of something. But when I do this, I can say that, hey, let's call this, we got to call this something. So the book calls it Z. I don't like that. So we've used A, B, C, D, E, F. We haven't used X. I like X. Why not? So let's go ahead and just call it X. Now, one thing that we are sure of is that these two are parallel right here with each other. And this is now, since we extended that, it basically functions as a line that is cutting two parallel lines, and we call that a transversal. So we know that this angle X is equivalent to this angle B, because if you turn your head to the side, if you need to, you can realize that this line right here that's going through them both, that's going through both those parallel lines, is a transversal. And then that X and B are both opposite interior angles, alternate interior angles. So we can say from this that B is equal to Z. They say Z in the book. I'm still stuck on that when I look at the two different ones. But I don't really like how little words that they use, so I want to make sure we explain why. So B is equal to X in this case because of alternate interior angles. Now, normally you should write the full words out, but in this case, I want to make this video kind of shorter. So B is equal to X because they are alternate interior angles. What's also nice about this is that we can say that our angle E is also equal to Z for the same reason. In this case, they use Z, I'm using X. But we can say that E is also equal to X for the exact same reason. But let me kind of highlight the transversal that we're talking about there. Remember, now we're looking at these two parallel lines. And this is now the transversal. So it's the skill in shifting your attention to one to another. And then from this, we can see that this is the same thing as that. That's why we're able to write that. And again, it's the same thing. Often we would write down which parallel lines we're talking about so they know what transversal we're looking at. But either way, it's usually enough to say something like this because a transversal intersecting two parallel lines creates an alternate interior angle, and they are congruent. It's a lot of words to say. The book's specific one was, if parallel lines are cut by a transversal, then alternate interior angles are equal in measure. So the idea of that, one thing that I don't like about this is that they use the word cut. That's not a mathematical term. It's more of a colloquialism. It's more of like something that we typically say. But again, it's used so much that we often say that, this transversal is cutting the between those two lines, or it's going through them. I like the word intersect. Call me a purist. I like the word intersect, or hits that line, which is also not a mathematical term, but I feel like it works too. There's nothing getting cut here. And this right here, B is equal to X and E is equal to X. Now, here's what's cool about this. There's something called the transitive property, which is what Ms. Tragle was talking about before. So transitive property. Transitive property, if A equals B and B C equals B, so if one thing equals this, so if A equals B and C equals B, right, then that means that, going back on this one, if A equals B and B equals C, then A equals C. Okay, now it's written correctly. I kind of jumped the gun on there. If A equals B and that same thing equals C, then A is equal to C. And this can show up in a lot of different forms, but we like to call it just the transitive property when we use it. So B is equal to X, and X is also equal to E. We can flip that around. Therefore, B and E are equal. So B equals E, which was our goal. Using transitive property, B and E are equal. So if you have two equations and they're both equal to the same thing, you can set them equal to each other, basically. And we've done that before, but we've called it the substitution property. So you could honestly call this a substitution property too. You don't have to call it the transitive property. You could say, all right, well, X is equal to B, so I'm going to substitute X here for B. It's up to you. The words in that case aren't really going to matter a whole heck of a lot. So this one right here is actually another one of those cases where we use an auxiliary line. So in a case like this, we can do it a couple different ways, okay? But we want them to relate to each other. So what I'm going to do, instead of drawing the line through here and then using those, instead of drawing that line right there, I could say that construct an auxiliary line that is parallel to AB and to CD, and put it between them. It's too many words. What we could do instead is we could use an extension. We can extend this. We're pretty used to extending these lines. So I could always extend this line. I like doing it like this. I could always extend this line right here. And then I might want to label a couple of these angles. So obviously I like X and Y, but X and Y are already taken. So and Z is already taken. Let's just do A and B. Okay. No, I don't want it to be confusing with that. So I'm going to use what the book goes with. It's W and V. Okay. So let's just do that. I would love to get creative here, but honestly, we're running out of letters. So right here, we have some of these things. Now we have a parallel line, a set of parallel lines, and a transversal that is hitting them both, that's going through them both, cutting them both, intersecting with both of them, whatever you want to call it. And we can use a couple of our properties for this. One of our properties could be that the exterior angle, this one right here, notice we have another one of those situations that looks like this. I'm going to try to draw it kind of like how they draw it, where we have a triangle and one of its sides is on a line segment or line or ray. So in this case, I'm going to say that this is equal to the opposite interior angles, or the remote interior angles, added together. And we can use that because we're not trying to prove that, and we've already learned it. So we know from this that Z is equal to V plus W, because the exterior angle of a triangle is equal to the remote or opposite interior angles of that triangle. Just kind of abbreviating it. Or the exterior angle of a triangle equals the sum of two interior opposite angles. There's a lot of words for it. Opposite interior, two interior opposite angles, whatever you want to call it. One thing that we can also use is the fact that this, let me highlight it so you can see which things I'm looking at real fast. From this same idea, we've got a transversal. We can realize that V has to be equal to X. Can you remember why? Just looking at the highlighted ones? I'm going to go ahead and write it that X is equal to V because they are corresponding angles. And you might want to put more words on it to say when you have a transversal cutting through two parallel lines that the angles that correspond to each other, corresponding angles are equal in measure. Okay. And similarly, we could extend even more stuff. We could let's look at this and see what else we can do. Let's take these things off and let's do that exact same extension idea. Let's do exactly that same extension idea and extend this. Come on, straighten up. Nope, not going to do it. We can also extend this right here and this right here a little bit, which extensions are perfectly legitimate, right? We could do that, try to figure out if that's helpful. Let me look at that just to make sure. I don't know if that's going to be super helpful for us. Oh, I don't even need to do that. I thought I would need to do that, but notice, these are vertical angles. We could say that W is equal to Y because they're vertical angles. We don't have to do any sort of constructions for a vertical angle like that. If we have two lines that are crossing, the angles opposite from each other have to be equal in measure. So in this case, if we know that W is equal to Y and X is equal to V, then right here, we can say that using the substitution property of equality, instead of writing V, we can write X. And instead of writing W, we can write Y. Notice I just replaced those with what they were equal to using the substitution property. And let's see what I was trying to prove. I was trying to prove that, so that's good. Sometimes I have to stop and say, what was I trying to do? That happens a lot. So in this case, they give you something like that. They give you a little bit of information about extending it. They label it the same way. That's where I got that. That's why sometimes I get confused on which letters they're talking about. But they're talking about extend the transversal as shown. What do you know about V and X? Well, V and X are corresponding angles. What do you know about W and Y? They're both vertical angles. And how does this help you? It helps me because if I know, if I have something, if I'm trying to say that Z is equal to X plus Y, I need to make a triangle of some sort because that's going to be the most helpful. Now, I could have done an auxiliary line and I could have done it a little bit differently. But the problem is that the wording and in a proof of an auxiliary line, how do you guarantee that goes through the vertex? You're going to have to label the vertex. You're going to have to make sure that you do that. You have to make sure that you don't imply that it's a bisector because there's so much overhead than just extending that line. It's not as elegant of a proof. Could you have done that? You could have done that. You could do it like this. See? Look, even the book's telling you there's more properties. They're like, but the wording is a little bit harder on something like that. So in that case, you'll have like if parallel lines are cut by a transversal, then the same exact stuff. Now they, in their proof on the next one, they kind of abbreviate a lot of stuff. I feel like you have to do a lot more definitions for something like this. But we can say that these two or corresponding angles, so that W equals Y. I'm not going to go through the whole thing. And then V and X are corresponding angles, so V equals X. So we get to use the exact same idea, we just labeled them differently. We could have used different letters for this. It didn't really matter, okay? And the one thing that we can do is we can say that Z is equal to V plus W, because they call this the angle addition postulate. And the reason, like, we know, we can look at this and say that that whole angle Z is going to be equal to the stuff I split it up into added together. Me putting a line between here doesn't reduce or change my angle. Me putting a line through it just means that I've broken it up into two segments, that like angle segments, sectors. I've broken it up in two sectors, but they still, when added together, will equal the original angle. So that's the angle, the angle addition postulate. That technically should have also been up here. Z equals V plus W for the exact same thing, you know? But either way. But the rest of the proof goes the exact same way. It's almost the exact same way. I'm going to let y'all work on that one. It's not super hard. This one is easier to grasp in our head sometimes, because we can look at it and say, obviously, Z is going to be V plus W. But it's about the words. It's about the words. These are going to be the exact same reasonings. This one will be angle addition postulate. I'll spell that out so you know how to spell it. And again, that just means that if you split up an angle, each one of its individual parts added together will be the original angle. That's all it means. And you can see it when you look at it. You can see it when you interact with it in real life as well. And that's all we really need. We're just going to make sure that we write the words out that says this is going to be the same reason as above. So go back a little bit if you want to see that writing, so I don't have to waste time. And almost everything is going to be the same otherwise. All right. This one is a little bit like yesterday's. Did we do it yesterday? Wait, didn't we do this one in the last video? This is almost the exact same one. What are they asking? That's a good idea to look at. In the figure to the right, we have our parallel lines. They're written with symbols. I don't need to highlight those. Each, like you can see from the vertex, I'll just do one, that this is parallel to this, and that's what this is saying. The line segment, which is what that symbol at the top means, with vertices A and B, that's what this part means right here, is parallel to the line segment with the vertices C and D. That's all it's really saying. We just need 2 points on a line segment to describe the whole line segment. Same thing with a line. And same thing with a ray, I believe. Let's look. And same thing for the other one. So prove that the measure of ABC, so the measure of angle ABC, so they're using the vertex, like that. So they're talking about that angle right there, is equal to this one. Now, I done thought we already did this the other day, but, you know, it is what it is. So instead of writing the measure of angle ABC and the measure of angle CDE, I'm going to call it X and Y, just to do less writing. Now, normally you don't want to do this too much in proofs, but still. So we want to kind of look at these individually. So let's look at this, and let's look at this. So notice I have a transversal right here. I have a transversal right there, which will tell me that this angle X and this are equivalent. So this is X. So now I'm going to call this Z just because we're going to use it a lot. It is actually, if you want to write it using their notation, the measure of angle BCD. Okay? Be careful about that. Let me just kind of clean this up a little bit. All right. So that, I'm just going to call it Z, though. So we know that X equals Z, and that's because the alternate interior angles. The full wording would likely be if parallel lines are cut by a transversal, then the alternate interior angles are congruent or equal in measure. There's a lot of words you could use. And what's interesting about this, if I turn my attention from that set of things and instead start looking at this one, which is an important skill to have, you realize I have two more parallel lines with the single chevron thing. And we can see that using alternate interior angles on this one, that y is equal to z. For the same reason, alternate interior angles on that other transversal that we have. And then we can say, because x is equal to z and y is equal to z, we can say x is equal to y using either the substitution property of equality, or we can call it the transitive property. They effectively do the same thing in this case right here. This is the point where I'm like, do I split this up into another video or do I not? It's me wasting time and making the video longer by deciding. Okay. Well, let's just start off by kind of looking at it and seeing if we need to label it. So they're using this little b degrees to represent their angle. Don't you love how they switch the notation every single time? So they're saying that they're calling this the angle at vertex B, and it's measured in degrees. There's a lot of information there. I'm probably going to need this. I'm probably going to want to do a c degrees right here for the same reason. You know, it doesn't really matter. But we know that this is parallel and this is parallel. So if you extend these, and honestly, this whole thing's called by constructions, but we haven't really constructed a whole heck of a lot, have we? We've really done mostly the same type of proofs that we've already been doing. So either I was doing really well and jumping you guys in early, or whatever. But that's what we're doing. We're extending lines, and that's kind of our construction. So maybe we write down that we extend the lines in the thing. And again, on this first one right here, I think they asked, is an auxiliary segment necessary? No, it's nice to extend our lines for visual reference, but we didn't have to extend. This one, we actually probably still won't need to extend it because we still have a line segment and another line segment that are parallel to each other and a transversal. So really, an auxiliary line's not necessary, but the extensions, they help our brain pan. But some things that we know about this, we know that B is equal to C in this case. I hope you see that they're alternate interior angles. So we know that they're equal in measure. I'm just going to write down alternate interior angles so I don't have to keep belaboring the point. So B and C are alternate interior angles. They're congruent. So we've got that part. We just had to give our words and use them right. Another thing that I can do is, I'm just noticing this by looking at it. I could take my attention away from that set, and then say, all right, well, here's a set of parallel lines right here, and here's a transversal. I know it's also a part of a different set of parallel lines, but all we need is two parallel lines to each other and a line cutting through it. That's all we really need. So I can tell you right now that C plus D are supplementary. And, you use more words than this, but if you have parallel lines and there's a transversal going through them, then we call this same side interior angles. So same side interior angles, which is what these are. These are on the same side and on the interior of our two parallel lines. And they're on the same side of the transversal. Same side interior. And we might want to list like which ones we're talking about to help somebody out. A lot of this side of things is going to be a kindness to the other person to make sure that they don't get confused. It's like if a teacher's talking to a student. So you guys get to pretend you're a teacher talking to students. or a student talking to a teacher about what they did on their homework. And we can also do the exact same thing since we know that C is equal to B, we can substitute that in right here to say that B plus D is equal to 180 using the substitution property of equality. I didn't even get that letter off. I went to write the Q and I wrote a G. Whatever. It took a lot of effort to get there, but it's a substitution property. And that's pretty much it. It seems like it's going to be way more complex than it actually is. Let's look at this one. Oh, it's our old friend that if you kind of turn it and you kind of put another one of these on top of it, it's going to look kind of like a star. But this was our old friend. It's not quite the same as our old friend from before where we found 5 different ways to do it. And I'm still counting new ways to do it. And y'all came up with a different way where you added up all the angles. And I'm like, y'all got to come up with a proof for that because I'm not sure where it is. That's the point. I'm going to make y'all come up with a proof one of these days for that. I need to know what you did so I can teach other students how to do it because, I'm not sure. It sounds great, but I haven't researched it yet. I don't have the time. I got teacher time. I don't have that kind of time to go look up how to do that. I'm kidding. I probably have already looked it up, and I'll probably have already made a video about it. You'll never know. You'll be able to look at this time at the top left here and know. Yeah, I haven't made the video, so don't call me out, all right? In the figure to the right, prove that D is equal to A plus C plus B. So A plus B plus C is allegedly equal to D. My goodness, would you look at that? I had no idea that this was the proof of that thing that you guys came up with. That whole thing I was just making a whole bit about. Turns out, y'all stumbled across this. And this is our chance to make a proof about it. So, you might have noticed that I drew an auxiliary line. I did. I'm extending this line segment kind of like I did in the previous proof. That was what I did, not what Mrs. Zenos did or what y'all did. But I went for proving it. So isn't that funny that the way I started off with it, I didn't even notice it, but it accidentally proved this bit right here. So let's look at it. And honestly, there's a little bit of stuff from Mrs. Zenos that it looks like in here too. So one thing that we do know about this, okay? We know we need a couple more labels. I need to label this new angle that was formed right here. That's going to help us a lot. So this angle right here, we know that it is an exterior angle. That Z angle is an exterior angle to this triangle. You might be able to see it a little bit better if I extend that line out. Then suddenly we have our old standby friend of a triangle whose one side of it is on a line or a line segment. But we know that it's equal to B plus C because exterior angles equal to opposite interior. Isn't that cool? Isn't that cool? And this comes up a lot. Once we really, really know all of these tools, you're going to be able to use whatever you want, whatever you feel most comfortable with. And there's a lot of ways to do this one as well. So I know that this exterior angle right here is equal to the opposite interior angles. That part's going to be useful for me. One other thing that I know is that this right here also forms a triangle on a line. So this D is an exterior angle with A plus Z. So it is also an exterior angle. But it's on a different set. Let me highlight it in a different color. So here is the triangle that I'm talking about. And here is the line that it's on. Do you see that? It's an exterior angle and it's equal to the opposite interior. And would you look at that? I know what Z is equal to, so I can go ahead and plug it in for Z. And that plug it in literally just means that I'm going to substitute it. We don't, in a proof and on the leap and things like that, we don't say the words plug it in. I know y'all think of it as you just replace it with something or you plug it in. But the thing is that the terminology we like to use to make sure everybody understands, because other people in other countries aren't going to understand. Other people in this country aren't going to understand plug it in. So when we say that, we want to make sure that we use the word substitution to make it to where it's easier for other people to understand us. So instead of writing Z here, I can write B plus C. That is the substitution property. And that's it. Look at that. We actually could have figured out from that previous problem that it was exactly the same. It was exactly the same. And let me think to myself if I still have that proof up. So we did that last one a lot of different ways. And was that in this one? Oh, yes, it was right here, but I don't have my annotations. I do have in, I believe, unfiled notes or presentations or annotations. I do have this where I annotated all the lesson plans. Yes, teachers have to do all of this. Feel bad for us. I even wrote the words oof on it. Nobody even saw this. So I made an auxiliary line. Oh, look at that. I went the exact way that they did. But notice we have these three angles. And we actually could have just added them up to find that out. And look how many steps I took having to prove it and then show it. I didn't actually need to do all of that when I could have just done this 3-line proof. Isn't that elegant? Anyway, y'all have a fantastic one, and I hope this video was helpful.